This paper is called the essence of the flyweight design pattern. So this is a work that I did with Caio Raposo, who is a student, a master's student who I advised here in Brazil at the Federal University of Minas Gerais. So what's the story of the paper? In 1998, Jens was working on that paper, the essence of the visitor pattern. At the time, I think Jens was a few years after that. I took the compiler construction course at UCLA, and Jens was, the teacher at the time, the professor who was teaching the course, instructor. And then he had all this fancy Java thing that would synthesize those visitors that were super cool, actually. And then at the time, I think Jens was a great fan of the visitor design patterns, a way to process programming languages. So in a way, I mean, the visitor, it brings to the object-oriented world something that's very common in functional programming. I mean, you want to fix the types, and you want to be able to vary the operations that you can perform on those types. So this is what we get with visitors. So essentially, we can. Here's an example of a visitor in Python. So we can, define methods for all the types that we have in our hierarchy of classes. And pretty much what visitors are doing is making something that's already native on a functional programming language. I mean, you have data types, this closed world. Like in the object-oriented language, you have this open world where you can always add new types. And then, on this functional-oriented world, we have this kind of closed world of types, and then it's easy to add new operations on them. And that's what we get with visitors. So, I mean, we can do this exercise of looking into those patterns that we have in the Gang of Four, and then we can more or less see which patterns are actually native in depending on the programming language. And you can find many of them. If you take, for instance, the strategy or the template method, essentially they are native in any language that supports functions as high order functions, first class functions as first class citizens. And then, so in this paper, we did this exercise. Okay, so let's talk about flyweight. I mean, that's a pattern that, people don't really talk much about it. So let's see, how can we make the flyweight design pattern kind of native on an object-oriented programming language? In a sense, essentially, I mean, you can make it native if you allow the memoization of the constructor of objects. An object is created by a constructor that's part of a class. If you memoize that constructor, essentially you are kind of adding to the programming language a native way of implementing flyweights. So, but the thing is that memoizing the constructor of objects may not be a good idea, because objects mutate. And so, if you, I'm not really sure if everyone understand that, but memoization is optimization, where you call a function and then you cache the result of that function, so that if you call it again, you just return the value that's stored there in the cache, the memoization table. So that's an optimization. So if you memorize the constructor of an object and you mutate that object, you are mutating aliases of that object that you created unintentionally, in a way. So just to give an example, I mean, this is a function in Python. I mean, it solves the knapsack problem, but I mean, what it does is really material to this presentation. You can memorize the function with this annotation, the cache annotation. I mean, that's one of the many ways that Python allows to memorize functions. But in this work, we are not really working in Python. We are working on another programming language called Hush. So Hush is a really cool programming language. I will show you the repository soon. It was implemented by one of the students in our university, Gabriel Bastos. So I will talk a little bit more about it. So we implemented memoization in Hush. So, but anyways, the idea is this. I mean, you call a function, you cache its result. If you call it again with the same arguments, you just return the cached result. So in Python, you do annotations, and then in our version of Hush, I mean, that's not official Hush, you have a keyword memo that really actually works on that in the runtime of the language to perform memoization. Our implementation of memoization is actually pretty efficient. I mean, it's likely to be more efficient than one in Python. I mean, at least when you compare similar benchmarks. Even though Hush is kind of slower than Python. It's slower than Python. Hush is implemented in Rust, but it's slower than Python. I mean, it's a scripting language, like Python, but slower. Anyways, so we want to implement safe memoization of mutable data, mutable objects into work. There are many ways of doing that, but let me just show what happens if you do this in Python. I mean, we can memorize a class in Python, like just add the annotation of the definition of the class. So in this case here, we have like points, have 2D points, we can memorize them. And then like if I create 2 points with the same argument, you know, P0 and P1, essentially they're pointing to the same memory because I mean, points memorized now. And then, you know, I can mutate P1. I assign to X, and that's fine. I mean, now P1 has a different value of the X coordinate. However, yeah, that changes P0 as well. And this may not be the intention of the programmer, in the sense that you created an unintentional aliasing between P0 and P1. So yeah, now they point to the same memory location. Anyways, so we have implemented safe memoization in Hush. I'll explain what safe means in this case, but just here, publicize the language a little bit. Hush is a shell scripting language. Was created 3 years ago here in our university. It has syntax that's very similar to Lua, which is another Brazilian language. So I mean, kind of similar. Similar in syntax, but not in purpose. So Hush is strongly typed, meaning that the programs are always, you know, well behaved if they are well typed. But it's dynamically typed though, like Python, Elixir, Lua itself, Bash, and this kind of languages. It has a garbage collector, and actually implementing memoization with the garbage collector was pretty interesting. And it has first-class functions. I mean, this will be important to us in this presentation. Anyways, Hush is kind of popular. I mean, if you go to, I went to the GitHub 2 days ago, and then I had like more than 600 stars, and has users like forks, issues, people submit issues. I think it's a very nice program language with a clean syntax. So I mean, if you guys want to take a look, there's a link of the repository right there. Anyways, so something interesting about Hush. I mean, Hush doesn't really have classes. Yet, you can kind of simulate object orientation. I mean, you can create objects as closures. So I mean, this function here simulates a class that creates counters. I mean, that's the syntax for dictionaries in Hush. So we can create this object as a closure on n. It's an argument of the function. So we can have like an attribute that refers to n, and we can have like methods which we associate with atoms, like get and inc. They are keys on this dictionary. So these are methods, and then we return this, and then essentially this function is, you know, is a class creating objects, pretty much. Anyways, and what's Flyweight? Again, this is a design pattern. Is a way to reuse some internal state of an object. I mean, you have an object, parts of it vary, but then have like some part that's common among many objects. So this we can implement that using Flyweights, this design pattern. I'm going to give an example here. I mean, that's not really an actual Flyweight, but it's just a simple way of explaining how that works. So imagine I have students. So students have names and identifiers, and each student is unique according to an identifier. And then we have courses, which are set of students. You can search students within courses. Of course, you should have just one student on each course, one version of each student on each course, of course. And then you have this registry class here that works as a factory, like an object factory. So whenever we create a student, yeah, there we go. First, you check if you had seen that ID before. If you had, I mean, you know that's saved on a table, like the memoization table. In that case, you return the student. Otherwise, you create a new student and then add that to the table as well. So, I mean, in a way, this is kind of a flyweight. I mean, that's how flyweights are essentially implemented. And in this case here, like students are unique per ID. And then the equivalent version in Hush is the program on the right side, I mean, in blue here. So here we are memoizing the function that creates students, and then we more or less get the same effect that we would obtain if we with the class on the Python class on the left. So I should be using Python because Python is more well known, but everything here is implemented in Hush. So how we get safe memoization? We have changed the runtime of Hush a little bit to obtain that. So essentially, we use shared pointers to guarantee the following. Whenever you try to memorize an object, you remove it from the memoization table. I mean, it's a very simple idea. I mean, this whole thing is just like an exercise on trying to get the essence of what's a flyweight. So anyways, let me give an example here. I mean, I have here this function that creates points, and then I create P0 and P1, and they have the same arguments, therefore they are memoized. I mean, that's how usually the heap would look like. I mean, we'd have like P0 and P1 pointing to this memory, which is a pair, and then like this memory, X1, X, and Y, and they are on the memoization table. And then in our case, I mean, we will access memoized objects through shared pointers. I mean, non-memoized objects are accessed using, just normal pointers. But then for memoized objects, there'll be these two hops, like one indirection, one level of indirection through shared pointers. And what do we get with that? If we have a new, reference, like P2 in this case, I mean, references now refer to the same shared pointer. And then, like all these pointers, like P0, P1, and P2, essentially, they are kind of like aliases in the sense that they ultimately refer to the same memory, which is memoized. But only P0 and P2 are logical aliases in this case. And then, like, if I modify P1, what will happen is that we'll create a copy of P1 outside the memoization table. So P1, like this copy, will not be on the memoization table. So essentially, you have like this copy on write semantics. And then, anyways, if you create new objects, they again will be created on the memoization table. So I mean, objects are always created on the memoization table, except if they are modified. In this case, they will be removed from the table. And then in this work, we have like a formalization of these properties using alloy, the alloy specification language. So that's something that Caio did very nicely. So I mean, you have a number of properties that he managed to demonstrate using alloy. So for instance, I will name 3 of those properties in here. And then the entire alloy script you can find in the extended version of this work. So first, I mean, the modification of an object, O, will cause a new object that I'm calling O prime to be created. And this object will not be stored on the memoization table. And O will remain memoized. I mean, the original version of O without modification will remain on the memoization table. And O prime will still be accessed through the same old shared pointer. I mean, once an object is memoized in our implementation of Hush, it's always accessed through a shared pointer, even if it's modified. So I mean, when you generate code for Hush, there is a small if-then else there for every object. I mean, is this object memoized? If it is, we implement access through two loads. We have to load first a shared pointer and then whatever the shared pointer points to. Otherwise, we access the object using just one load. So, but what's interesting is that this implementation, it doesn't really seem to incur on any noticeable performance penalty. At least we haven't really seen anything like that. I'll show a few experiments. So, I mean, in the extended version of this paper, we have 4 research questions. In this paper, I will go briefly over 2 of them. So first, I mean, the first question is just to demonstrate that our implementation of memoization is not really straw man. I mean, it's very efficient. I mean, you get, those performance boosts, like you can make an exponential function run in linear time with memoization. So, I mean, if the function is referentially transparent. But I think that our benchmarks, like the object-oriented benchmarks, it's hard to think about like benchmarks where you get those gains. I mean, so we have this RQ1 just to show that we can get like huge performance boosts out of memoization, and then we have RQ2 just to demonstrate that once we memorize object-oriented benchmarks, the performance penalty compared to unsafe memoization is minimal. Okay. And then in the extended version of the paper, we have two more research questions. So one of them is what's the impact of hashing on the efficiency of memoization? Because, I mean, to memorize the objects, we need to do deep hashes. Like, sometimes an object refers to other objects, and then have to compute hashes of hashes. So have to, what's the impact of hashing in this case? And then also, what's the interplay between memoization and garbage collection? In principle, we should not trace the memoization table with the garbage collector. And so there's a trade-off. I mean, if you start memoizing a lot, I mean, there'll be maybe like a logical memory leak because the memoization table is not traced. But if you trace the memoization table, then you have a huge slowdown because, I mean, the table may be huge. Anyways, so I mean, on this paper, I will just go a little bit over RQ1 and RQ2. So first thing, like, is our implementation of memoization efficient? So Caio has a repository with a number of benchmarks. So 7 of them are like referentially transparent functions. Here's an example. I mean, this is Fibonacci. So this function is exponential on n, like on the number of bits of n. You have like an exponential running time. But however, once you memorize it, you get back the linear running time on the number of bits of n. So I'm sorry, not on the number of bits, but on the value of n. So I mean, it's like this is like the kind of the hello world of memoization, and so I mean, we get like the nice numbers. So what happens if we memorize object-oriented benchmarks? We have 6 benchmarks in the Hush repository, which are kind of object-oriented. I mean, we create objects with them. So, and then we have tried 5 different implementations of memoization. So, well, the first is not really memoization, it's just the original Hush. I mean, to this day, Hush doesn't really incorporate memoization. So if you go to the official Hush repository and get it and check it out, I mean, there'll be no memoization there. So I mean, that's the original version of Hush, which is implemented in Rust. Okay. And then have unsafe memoization, meaning that you can get like an intentional aliasing and you don't do anything. I mean, you access objects as before, and then you may have programs that may not be really what you want to write. And then have guard and memoization in the sense that you have anything else there. And if you try to modify an object, you stop the program. You trigger an exception, and that will stop the program. So I mean, it's still, I mean, no shared pointers, but there is a guard. I mean, you can't modify an object that's marked as memoized. You can't do that. And then you have an implementation of shared pointers as a library. So in this case, we implement like shared pointers. You simulate them using like sets of objects that point to the same, kind of. We have sets of objects which are logical aliases, so that in a way kind of simulates the shared pointers. But this implementation will be very slow. I mean, if you don't really touch the runtime of the language, it's hard to have an efficient implementation. And then have our implementation with like shared ownership pointers. So we have an if then else to check if an object is memoized or not. If it is, we have to load it twice, like a pointer to get like the final memory that object, that reference points to. So first benchmark, just like a simple benchmark that create polygons. It has a very cheap constructor. So basically, like what this benchmark is doing, like it's taking like a list of points and then creating insert them in the set that defines polygons, and then at some point to try to see like if a ray crosses those polygons. But anyways, most of the complexity is in creating the objects, but creation of objects is simple. I mean, you create lots of objects, here like 6,000. And then in this case, what happens is that we don't really get anything on top of memoization because the constructor is kind of cheap. Something that is interesting is that even though we don't really get any performance improvement on top of the original hash with memoization in this case, we are not doing much worse than unsafe memoization. So essentially, like we're doing the same. If you try to implement memoization as a library, like shared ownership pointers, as a library, in this case, yes, there will be a slowdown, observable slowdown. And this doesn't really vary regardless of the number of objects that collide in the memoization table. I'm here measuring the number of collisions and have like almost like 100% of collisions at some point, and the performance is still pretty much the same thing. So, bottom line here is that you have to memorize objects that have like expensive constructors usually. So let's try a new object, a new benchmark. It's time. Using the polygons. It's time to implement figures, and then like we have like more complex figures that we can create out of those polygons. So have intersections and unions of figures, and in this case, the constructor is way more complex. So again, I will be reporting time per number of objects that we create using our 5 different implementations of memoization. So first thing, the original version of Hush will be slower. So memoization in this case will pay off. You have a faster implementation. And again, there's not really any difference between unsafe and safe memoization in this case. Regardless of the number of collisions that we observe. So the things that we can implement safe memoization of flyweights in a very efficient way. I wonder if there is someone trying to ask a question there because I can hear something. Maybe not. Anyways, continue. So just concluding now.
Can you hear me, Fernando? Okay, yeah, go ahead. Yeah, you were running
Yes.
over time.
Oh, I'm sorry. So just concluding, we have presented a new technique to memorize the functions of mutable objects. Our implementation is available in this repository. And well, there's a lot of things that we can do here, like improving like the interaction between garbage collection and memoization, evaluating the cost of hashing, implementing like maybe memoizing hashes would be something cool. We would like to implement at some point automatic memoization, but that's future work. So I'd like to thank Caio. He did this into his master thesis. He came from the north of Brazil to Belo Horizonte, so it was a privilege to have him here. And I need to thank the Brazilian Ministry of Education as well for funding his scholarship. And that's pretty much it that I had to say. So thank you very much, guys.
Does anyone want to ask a quick question?
I wonder if you guys have questions.
So I think it's wonderful, this thing with the rust underneath. Is the rust thing helping you, or are you working totally above the level where rust has an influence?
Yes, yes, Rust is absolutely helping us. We got the shared pointers out of Rust. That's part of the Rust standard library. So we could get that into the runtime of Hush because Hush was implemented in Rust. Were it not, well, if we were implemented in C++, we could get that as well because there is C++ has that as a library, but otherwise we'd have to implement it ourselves. Another thing, we chose Hush, not Rust, Hush, because it creates objects as functions, as closures. So by memorizing the functions, we get to memorize the class. So we chose Hush out of that. And because it's implemented in Rust, it was easy to implement shared pointers, to add shared pointers to the runtime of the language.
Yeah. Oh, that's cool. Anyway, Fernando, thanks for everything.
You're welcome, yes. Guys, academic brothers, other questions? Okay, so I think that pretty much settles it. Is that right?
Yes, sorry, my mic was off. Yeah, yeah. Thank you very much. Okay.
Okay, guys, thank you very much for your time and have a good workshop.